Welcome back, guys. We're going to continue with our equilibrium problems. Now we're going to look at problems where we have things hanging. The simplest case of this is something that's being suspended at an angle and at a side. So our picture here has something that has been being suspended by two wires. One is straight horizontal, so it only has an x component, and the other one is directed at 50 degrees with respect to the horizontal. So I'm going to make a free body diagram, and I'm going to choose to do this on a dowel. I have a force that is holding the sign sideways, which I'm going to call T1. I have a force that's directed in the same direction as this string, which I'm going to call T2. And then the sign itself has a weight associated with it that I'm going to call mg. The next thing we have to do is get rid of this angle. So we shouldn't like this T2. So T2 that's at an angle should be able to be resolved. And I can resolve this into T2 cosine of 50 and T2 sine of 50. And then I'm going to write down my Fnets. So in the y direction, Fnet is equal to 0. And I have one arrow up and one arrow down. Our arrow up is not T2. It's T2 sine of 50. Because T2 goes both up and over. Our arrow down is just mg. So I'm going to get mg by itself. And then divide both sides by sine of 50. So this will tell me what T2 is. Plug in our values. I have 100 kilograms. I have 10 meters per second squared. Sine of 50. I'm going to grab my calculator, make sure it's in degrees. And I get 1305. Again, I don't make this negative because we already subtracted the weight. So we're already taking into account that it's going down. Once I have this, it'll be easy to get the x direction. In the x direction, Fnet is also equal to 0. And in this case, I take right minus left. Going to the right, I have this component of T2. Going to the left, I have T1. So T1 is going to be equal to T2, which we said was 1305, times cosine of 50. Which is about 839. All right, I talked about this problem in one of the Google Meets with you guys. This is a case where the tensions are the same. And so I can call both of them T. So I have somebody walking across a wire, a rope, and the angle is the same. So that means that our forces are going to be her weight going down and then tension going this way and tension going that way. So those two are balanced. And actually, I should make those tensions much longer because their two y components together need to add up to this arrow down if I'm doing things to scale. So I should probably extend them almost all the way to the edge. All right, I need to find these components. So we don't want to have anything at an angle. So I'm going to do that right here. I have t. Now they're telling us this is 10 degrees. So this is going to be ty, which is the opposite side. So it would be t sine of 10. This is going to be tx, so this would be t cosine of 10. We have the same thing for the other side. So I'm going to consider the y direction because the only information that I really have numerically is her mass, which acts in the y direction. I'm going to say that in the y direction, Fnet is equal to 0. My forces are balanced because she's at rest. So we're saying we're taking the moment right when she's right there. She stopped. And so I'm going to take my ups minus my down. So in this case, I have two things. Each one of the sides are going to hold up half of her weight. So I'm going to have t sine of theta, which is t sine of 10 degrees, plus t sine of 10 degrees minus mg is equal to 0. So each one of these components is holding up part. I'm going to combine those together and take weight to the other side. So I have 2 times t sine of 10 degrees is equal to mg. And so t would be equal to mg over 2 sine of 10, which is going to be 50 times 10. Again, we're not putting in the negative because we already did. We subtracted. And 2 sine of 10. When you put this in your calculator, you want 50 times 10 divided by 2 divided by sine of 10. Or divided by parenthesis 2 sine of 10. And I get that my tension is 1440. All right. In this one, we know that the tension is 4,500 newtons. In that direction, the force that they're pulling with, we don't know this, and we don't know that. And you want to find the force of B. So what I'm going to do is get the components. So I know that F of A, and this isn't a free body diagram, so I am free to draw on it. This side here is going to be F of A times the sine of 48 degrees, because that's the opposite side. For F of B, and I'll change colors, that's going to be this one. I should make it dotted. And this is the opposite side. So this is going to be F of B sine of 32 degrees. Now, as they pull, it's going at a constant speed up. It's not going side to side. So in the x direction, Fnet is equal to 0. In the y direction, F net equals equal to 0 because it's constant speed. I'm sorry, in the y direction, it's F net equals 0 because it's constant speed. In the x direction, it's F net equals 0 because essentially it's at rest. It's not moving. So I'm going to take my right minus my left. So I'm going to have F B sine of 32 minus F A sine of 48 is equal to 0. I know FA, it's 4,500. So I'm going to get FB by itself. FB is going to be FA sine of 48 divided by sine of 32. So this is going to be 4,500 newtons sine of 48 divided by sine of 32. I'll plug this into my calculator. I'll stand out of the way as well. And I have 6,310. Actually 11, so it's 0.68, so I should round that up. So 6,311.